I want to start by going back to something we did last week and just doing a quick recap since we had a bit of a diversion on Friday. So if you'll think back to, not Friday, Thursday, sorry. Think back to, I don't know, it's probably Wednesday. We generated a second order differential equation and then worked our way to a solution. And that started with the basic concept of a simple harmonic oscillator based out of a spring mass system, where I have a mass of value m and a spring constant of value k. We started by saying in this system, if we wanted to understand how the system behaves, we use, I guess you're going to want to understand how the system behaves. One of the most tried and true ways to do so is to start with Newton's laws. So this requires that we take our system and displace it. We did, and the motion of the system has to be described by this relationship between the acceleration and the position. We did a little bit of algebra, a little bit of substitution, and we wrote this as a second order differential equation, which states that if you take the derivative of our function twice, you will generate an equation that, when the derivative is taken twice, produces the original function, a constant, and a negative sign. We then went through the process of trying to find a function that would do that. We just guessed. But in guessing for our function, we actually developed three functions because they represent the first and second derivative of our main function. We used cosine as our starting place, but we didn't have to. We could have used sine, but we felt that in dealing with our system, this one matched more what was happening because we began with a displacement at time equals 0. So this seems to work out because cosine begins at a displacement at time equals 0. We took the derivative, generated a new relationship that produced the sine. And if you look at a lot of what we did on our lab last week, you should be able to see quite clearly that the position and the velocity function are often in opposite directions. And this kind of states right from the beginning that if you pull the object out to the right, its initial velocity is going to be to the left. That's what that negative sign says out front. Take the derivative again, the negative sign stays. We bring out another one of our omegas from inside our function. And there it generates three functions. Now, I wouldn't leave them like this because this is very much tied to the spring mass oscillator. But one of the things that we know is common to all of them is that square root of k over m term. And that term has to be in radians per second. So this term is often called the angular frequency. For a spring mass, that's going to be the square root of k over m. But for every single oscillator, there will be something else that controls the oscillation. In fact, it will be your job to figure out how to take a system using Newton's laws and figure out how it oscillates and which of the behaviors of the system control the oscillation. So what we're going to do is rewrite these in a generic form. That puts omega in here because every oscillator is going to have the same behavior, and there will be something that physically controls the motion of the oscillation. So by making these generic, it applies to every simple harmonic oscillator, not just the spring mass oscillator. All we need to know is that for each oscillator, there will be a different value for omega. And there's more to it than just that. We also have a few other little things here that I want to make sure you have in front of you. For example, these are sine and cosine functions. Because they have only a value between 1 and -1 from here to here, which means that whatever number's out front is the maximum of the function. So those represent the maximums of the function. So Vmax for every oscillator will be x naught omega, and Amax for every oscillator will be x naught omega squared. And for a spring mass, that's, pretty clear, x naught times the root of k over m. And for acceleration, it's x naught times k over m. And we just sub in whatever our value is for omega. There's one more thing that we need to put up here, and that is the time that it takes to repeat itself is all contained within here, because the time it takes to repeat itself is how long it takes this portion of the system to advance by 2 pi. So the period was defined as 2 pi divided by omega. That works great for things that oscillate slowly, but we also define the frequency, which is for things that oscillate fast, as 1 over the period, which would just be omega divided by 2 pi. Which shouldn't be much of a surprise, because if you take omega and divide by 2 pi, you're dividing out by the number of radians, which is going to give you oscillations per second. So this tends to be in 1 over seconds or hertz, the unit of frequency. And like I said, if you want to put it in for a spring mass, that's going to be 2 pi times the root of m over k, or 1 over 2 pi times the root of k over m. All right, a box is going this direction at 1.5 meters per second, has a mass of 5 kilograms. This box has a mass of 2 kilograms, and there's a spring of spring constant 100 newtons per meter. There's no friction in the system, and t equals 0 represents the moment the 5 kilogram box strikes and sticks to the 2 kilogram box. When does the system come to rest? Where does the system come to rest? And how much energy does the system have? There's clearly a collision, right? But the question asks, when does this system come to rest? After the collision, the spring is going to bring the system to rest. It's going from its equilibrium position, where the spring is not stretched or expanded, to maximum displacement. And that's a period, that's 1/4 of the total period. So the time it takes to come to rest can be based on the period of the oscillation of the system. And we only see 1/4 of an oscillation. We don't have to do hardly any work here. No, that's going to be 1/4 times 2 pi times the root of m over k for a spring mass oscillator. It's 2 pi over omega, and omega is square root of k over m. So just doing a little bit of algebra and subbing in what we have here, m is going to be 7, and our value for k is 100. Quite literally 1/4 of a period, just like we talked before, just with numbers. Where does the system come to rest? Oh, come on, come now. That's first semester stuff. Really? You can't figure out where the system comes to rest? Maximum displacement of the spring? Because that's what you need to figure out, the maximum displacement of the spring. Probably you'd have to figure out how fast the system's going after the collision. So that is a perfectly inelastic collision. So let's figure out what our speed is right after the collision. Momentum's conserved in any collision. So I can figure out this velocity by doing conservation of momentum. Again, first semester. So 5 times 1.5 equals 5 plus 2 times whatever their combined velocity will be. And this will be V max. Because this will be the fastest the system goes. The spring slows it down every moment after that. So my V max is going to be 5 times 1.5 divided by 7, or I think it comes out to be 1.1 meter per second. But if I want x naught, well, I could use conservation of energy, or I can remember that V max equals x naught times omega. So x naught equals V max times the square root of m over k. Divide both sides by omega. I said, or do conservation of energy, first semester. You can use the second semester stuff, though. We know it now. So this will just be 1.1 times the square root of 7 over 100. Any question about that? Yep.
Is the angular frequency like k over m or m over k?
The angular frequency is the square root of k over m. But when I divide it by both sides, I get square root of m over k. Does that make sense? Okay. Energy is just energy, so I'm probably going to use 1/2 mv squared to figure out the energy of the system after the collision. That seems like the best way to go. I mean, you could use x naught, because you have it now, and do that the total potential energy is 1/2 k x naught squared. Just take your pick one of them. You're going to get the same answer. They get harder than this. This is just kind of showing you the ropes a little bit about how this stuff's going to work. Maybe, go ahead.
Can you explain again why we used 1/4 t to find the time?
Sure. How much of an oscillation occurs in the system after the collision to find out where it comes to rest. This stage here is the equilibrium position. The spring is still in its relaxed state. We haven't started moving yet. I'm sorry, we haven't started compressing the spring yet. So there's another picture. I didn't draw it, but another picture where the system has come to rest. So consider this moment here, where this box and this box have compressed the spring, but now the velocity of the system is 0. How much of an oscillation is that, going from equilibrium to maximum compression?
Thank you.
You're welcome. Now you could also use a motion equation if you want. I mean, it's okay to do that. You could say V equals negative x naught omega sine omega t. When does this go to 0? Right? You could do that. But you'd have to understand that that's not necessarily the time you're looking for. But we know that it's going to be one of the times. Just figure out which one you need, because there's going to be multiple times when the velocity comes to 0. I just think knowing that it's 1/4 of the period is probably the best way to go. Now you could ask another question, like how long does it take until the spring shoots the masses to the right? That'd be half a period. Right? If the boxes don't stick to the spring, if it compresses and then comes back to equilibrium, it's half a period. Same kind of problems. Let's try another one. This is going to be one of your homework questions. It is deceptively hard. Problem like this, where you drop a box onto a spring and it sticks to the spring. We had this problem first semester, and there's some deceptively hard parts about this problem. But the problem we had first semester was mostly about energy and net force. Didn't have anything to do with what's happening in this, in time. So if the box sticks to the spring, asking how long it takes, asking stuff like how long does it take for the spring to compress, that's going to be something that's related to the period. So if you go back to your homework in November, when we did conservation of energy, just think about the kinds of problems that you would have in there that involve a cart or something hitting a spring. They all can have some kind of component related to simple harmonic motion.